For years, it was introduced as one of the most spectacular planets ever found. A hidden world wrapped in rings so enormous that their modeled radius was roughly 200 times the radial extent of Saturn's main rings. There was only one problem. No telescope has ever seen the planet. No telescope has ever photographed the rings. What astronomers actually recorded was the light of a young star called J1407. In 2007, that star faded through a bewildering sequence of eclipses lasting almost 2 months. At the deepest point, at least 95% of its light disappeared. The brightness changed in sharp steps, as though dense bands, transparent gaps, and crisp edges were sliding across the face of the star. Years later, researchers reconstructed one possible explanation: an unseen companion surrounded by 37 vast rings extending about 90 million kilometers from the center. That reconstruction became the famous image of J1407b, sometimes called Super-Saturn. But the image is not a photograph. The 37 rings are not 37 observed rings, and J1407b is not a confirmed planet. The eclipse has never repeated. Searches with some of the world's most powerful telescopes have not found the proposed companion. Dynamical models have shown that keeping such a huge ring system intact would be extraordinarily difficult. And a promising millimeter wave source detected in 2017 disappeared when astronomers looked again in 2024. Something real crossed J1407. The starlight proves that. But what crossed it, whether it was bound to the star, and whether the famous giant ring system ever existed in the form we imagine, are still open questions. This is the complete story of J1407. What was directly observed, what was reconstructed from a light curve, what later searches ruled out, what remains possible, and why the most famous ringed world beyond our solar system may also be one of astronomy's most misunderstood mysteries: the eclipse that made no sense. Every part of this story begins with a single star and a few weeks of strange light. The star is officially catalogued as 1S WASP J140747. Astronomers mercifully shorten that to J1407. It also carries the variable star name V1400 Centauri. It sits in the constellation Centaurus, and it is not a remarkable star in itself. It is a little smaller and cooler than the Sun, roughly a K-type star, and it is very young, around 16 million years old. For comparison, our Sun is over 4.5 billion years old. J1407 is a stellar toddler. That youth is not a detail. It is central to everything that follows. J1407 belongs to the Upper Centaurus Lupus part of the Scorpius-Centaurus Association, the nearest large association of young stars to Earth. Stars this young can still retain debris from formation, and giant planets may still be assembling moons inside disks of gas, ice, and dust. Modern parallax measurements place J1407 about 450 light-years away. For most of astronomical history, nobody paid this faint young star any attention. What changed that was a survey called Super-WASP, the Wide-Angle Search for Planets, a project built to watch huge numbers of stars at once, looking for the tiny, regular dips in brightness that reveal a planet crossing in front of its star. Additional monitoring came from the All-Sky Automated Survey, ASAS. Between them, these projects were quietly recording the brightness of J1407 night after night, and in the spring of 2007, J1407 did something no ordinary star should do. It began to dim, not in the shallow, clean, symmetric way a planet produces when it crosses its star. A small dip, a flat bottom, a return to normal. This was something else entirely. Over a period of about 56 days, centered near the end of April 2007, the star went through a long, deep, and bewilderingly complex series of eclipses. At least 5 major multi-day dimming events appeared in the record. The light dropped, recovered, and dropped again. At its deepest, the star dimmed by more than 3.3 magnitudes, leaving only about 5% of its normal visible light, and the eclipse contained structure inside structure, sharp changes over hours, broad dark intervals over days, and partial recoveries between them. Here is the crucial point. An ordinary planet passing in front of a star cannot produce this pattern. A single spherical world creates a comparatively simple transit. To block nearly all of the light, remain in the way for weeks, and produce so many abrupt changes, the occulta had to be far larger than a planet's solid disk and internally structured, with opaque regions, translucent regions, and gaps. J1407 is magnetically active, and star spots normally change its brightness by several percent as the star rotates every few days. But star spots cannot explain a loss of roughly 95% of the light or the sharp eclipse edges. The team also checked the nearby stars and the behavior of J1407 outside the event. The extraordinary dimming was not an ordinary stellar fluctuation and was not easily dismissed as a simple instrumental error. At the time, the event passed unnoticed inside a huge archive of survey measurements. It was recognized years later when Mark Bacall, Eric Mamajek, and their collaborators examined the Super-WASP and all-sky automated survey records of young stars. Their study presented a complex eclipse centered on the 29th of April 2007, with significant dimming occurring on and off for roughly 54 to 56 days. The result was published as a candidate occultation by an extended disk around a secondary object. The researchers compared it with rare long eclipse systems such as Epsilon Aurigae, where a large disk rather than a bare stellar or planetary body blocks the light. They did not begin with a photograph of a planet. They began with a time series, brightness measurements, missing daylight intervals, weather gaps, and one extraordinary event. Whatever had crossed in front of J1407 in 2007 was large, structured, and unlike a planet. And it raised an immediate, difficult question. What could block a young star in such a complicated pattern for nearly 2 months? Building a giant ring system from starlight. To understand the answer astronomers proposed, you have to understand what a light curve can tell you and what it cannot. A light curve is simply a graph of a star's brightness over time. When something passes in front of the star, the light drops, and the exact shape of that drop encodes information about the thing doing the blocking. This is the foundation of transit photometry, the same technique used to find thousands of exoplanets. Normally the shape is simple because the blocker is a simple sphere, but the shape of the J1407 light curve was anything but simple, and its sharp, sudden changes carried a specific kind of information. Think about what happens when the edge of something opaque sweeps across a star. Because the star is not a point, it is a disk with a real size. The edge takes a certain amount of time to cross it. That crossing time sets a kind of natural resolution. When the brightness of J1407 changed very sharply, over intervals as short as hours, it meant that a sharp edge was sweeping across the face of the star. A soft, fuzzy blob cannot produce a sharp gradient. A crisp edge can, and the light curve of J1407 was full of them. Astronomers led by Matthew Kenworthy, working with Mamajek, took those gradients and worked backwards. If sharp edges were crossing the star, then the object had sharp-edged internal structure, regions that were dense and opaque, separated by regions that were nearly empty, concentric dense regions with gaps between them crossing a star. That is the description of a ring system. By modeling the timing, depth, and steepness of the observed features, Matthew Kenworthy and Eric Mamajek reconstructed one possible geometry: an enormous, tilted system of concentric bands crossing J1407, centered on an unseen secondary object. Their 2015 best-fitting model contained 37 rings. That number is often repeated as though 37 rings were individually photographed. They were not. 37 was the number of radial zones in one model that reproduced the available light curve. The scale that came out of the model is what made the object famous. The reconstructed outer radius was about 0.6 astronomical units, or roughly 90 million kilometers. The full diameter would therefore approach 180 million kilometers. That is wider than Earth's average distance from the Sun. It is from this model that the famous comparison came. The candidate structure had a radial extent roughly 200 times that of Saturn's main rings. The comparison refers only to how far the modeled material extended from its center. It does not mean the system was measured to contain 200 times Saturn's ring mass, brightness, or number of rings. The same model estimated a surprisingly large amount of material, under assumptions about the surface density and opacity of the bands. The total mass was on the order of 100 lunar masses, roughly comparable to the mass of Earth. That estimate is highly model dependent. Change the particle sizes, thickness, opacity, or incomplete parts of the light curve, and the inferred mass changes as well. One especially clear modeled gap appeared about 0.4 astronomical units from the center. The researchers proposed that a satellite smaller than roughly 8/10 of Earth's mass might have cleared it. This became one of the most exciting claims. A possible exomoon inferred from a gap inside an inferred ring system around an inferred companion. Every step was scientifically motivated, but every step added another layer of uncertainty. That limitation is the one most often lost. Reconstructing an object from a light curve is not the same as photographing it. The observations were interrupted by daylight, weather, and the normal cadence of ground-based surveys. Across the full eclipse interval, only about 11% of the time had usable photometric coverage in the detailed ring modeling study. Large grey regions in the published reconstruction mark radii where no data directly constrain the bands. Different ring arrangements, disk orientations, transit speeds, and optical depths can produce similar measurements. The model was a physically motivated solution, not a unique map. Continuous space-based coverage of the entire event could have sharply reduced the ambiguity. The 2007 record cannot. There was also a subtler point about what kind of structure this would even be. A mature ring system, like Saturn's, is thin and settled. The J1407 model implied something much larger relative to its central object, a structure filling a large fraction of the region where the object's gravity dominates. Rather than a finished set of rings, this looked more like a young, thick, still evolving disk of material around a substellar object, the kind of disk in which moons are thought to form. The gaps were tentatively interpreted as lanes possibly swept clear by forming moons, exomoons in the act of being born. Later, dynamical work showed that at least one gap-like feature could also appear temporarily when a heavily disturbed disk is stretched during a close passage to the star. A gap, therefore, would not, by itself, prove that a moon existed. So by around 2015, astronomers had done something remarkable. From nothing but the flickering of a distant star, they had reconstructed a candidate structure of extraordinary scale and detail, and given it a name, J1407b, the proposed ringed companion. But reconstructing a structure is not the same as seeing the object that carries it. They had a model of the rings. They had never detected the planet, and the natural next step was to go and find it, searching for J1407b. If a giant ringed object is bound to J1407, it should influence the star, glow with its own heat, or eventually reveal itself in an image. Astronomers therefore searched for the body behind the model. The name J1407b can be misleading. The letter B follows the normal naming style for a first proposed companion, but it is not a certificate of confirmation. In this case, J1407b is shorthand for the unknown object that might have carried the occulting structure. It may have been a planet, a brown dwarf, a free-floating object, or something that does not fit neatly into those categories. Early interpretations placed the possible companion somewhere in the broad substellar regime. Some orbital solutions suggested masses of several to a few tens of Jupiter masses. Around 13 Jupiter masses is often used as a rough deuterium-burning boundary between giant planets and brown dwarfs, although formation history also matters. The uncertainty was therefore not merely about the mass. It was about what kind of object astronomers were searching for. One method was radial velocity. A massive companion orbiting J1407 would tug the star back and forth, producing small Doppler shifts in its spectrum. The measurements did not reveal the clear periodic wobble expected from many massive, close configurations. They excluded portions of the possible mass and orbit space, but did not identify a unique orbit. Another method was high-resolution imaging. Researchers used the Very Large Telescope in Chile, the Keck telescopes in Hawaii, and sparse aperture masking, a technique that can separate a faint, nearby source from the glare of a bright star. These searches found no companion. The 2015 mass and period study placed meaningful limits on a bound object. If the orbit was circular, the allowed period was narrowed to roughly 3.5 to 13.8 years, corresponding to orbital distances of about 2.2 to 5.6 astronomical units. Across those periods, companions more massive than roughly 80 Jupiters were ruled out at the stated confidence level. Large regions of the lower mass parameter space were also excluded by direct imaging, depending on separation and model brightness. Those numbers should not be mistaken for a measured orbit. They are conditional limits. A highly eccentric orbit, a different viewing geometry, a lower mass, or an object hidden too close to the star at the observing epoch could evade a particular search. Young giant planets and brown dwarfs also cool and fade, and estimates of their infrared brightness depend on evolutionary models. Later, thermal infrared observations with the NACO instrument also failed to reveal a central body near the candidate millimeter source discussed later in this documentary. At the location of that source, the imaging was sensitive to young objects of roughly several Jupiter masses, yet no object appeared. Once again, the observations constrained the possibilities without delivering a detection. Precise astrometry provides another possible route. A sufficiently massive bound companion could shift the position and motion of J1407 on the sky. Gaia has measured the star's distance and motion extremely well, but no published astrometric detection has established J1407b as a bound companion. Future astrometric solutions may tighten those limits, especially when combined with radial velocity and imaging. This distinction matters because public lists and old illustrations can create a false sense of certainty. J1407. B still appears on some catalogues and educational pages because it is an important candidate and because the name is convenient. Catalogue inclusion does not turn a model into a confirmed planet. NASA's widely shared image is explicitly an artist's conception. A single non-detection never proves that an object does not exist, but repeated non-detections from different methods are cumulative. A massive closed brown dwarf should tug the star. A warm young giant sufficiently separated from it should glow in infrared images. A bound orbit should eventually produce a repeat, or at least remain dynamically plausible. Each failed search removed another part of the map, and the most damaging absence was not a missing point of light. It was a missing eclipse. If the same giant structure circles J1407 on a closed orbit, it should eventually pass in front of the star again. It never has. The eclipse that never came back. A bound ring system should repeat. The period might be years or decades, and the geometry might cause some eclipses to be missed. But a closed orbit makes a basic prediction. The occulter comes back. Astronomers therefore watched J1407 forward in time and searched backward through the historical sky. Modern monitoring combined observations from several ground-based surveys and telescopes. The star's ordinary behavior was easy to recognize. Dark star spots rotating across its surface produce a brightness modulation of about 5%, with a dominant period near 3.2 days. A longer magnetic activity cycle lasts about 5.4 years. After modeling and removing those signals, a 19-year photometric study found no plausible periodic transit by another companion, and no second event resembling the eclipse of 2007. The historical search reached much farther. Astronomers inspected 387 photographic plates from Harvard, Bamberg and Sonneberg, covering parts of the period from 1890 to 1990. No earlier deep eclipse was found. When those plates were combined with modern observations through 2018, a large fraction of candidate orbital periods between 5 and 20 years could be rejected. The result did not mathematically eliminate every bound orbit. The coverage was incomplete, and an eccentric orbit with the wrong timing could still avoid the available measurements. But the simplest repeating picture was becoming difficult to maintain. The only spectacular eclipse in more than a century of partial records remained the one observed in 2007. Then came the dynamical problem. Could a structure this large survive around an object orbiting J1407? The first useful concept is the Hill sphere. This is the region around a companion where its gravity can hold material against the competing pull of the star. The proposed disk occupied an unusually large fraction of that region. As the companion moved through an eccentric orbit and approached the star, its Hill sphere would shrink. Material near the outer edge could be stripped away. The second concept is the Roche limit. Inside this limit, tides can prevent loose material from assembling into a moon. Saturn's main rings sit close to this kind of regime. The modeled J1407 structure extended far beyond the scale of a compact mature ring system into territory where particles would normally be expected to collide, spread, and form moons. This is why researchers often called it a circumplanetary or circumsecondary disk in transition, rather than a finished Saturn-like ring system. Numerical simulations made the tension sharper. A 2016 study tested a companion on the eccentric orbit needed to match the speed and duration of the 2007 eclipse. Rings moving in the normal prograde direction were stripped too efficiently and could not reproduce a long-lived system of the required size. The most stable solutions were retrograde. The disk material orbited the companion opposite to the companion's motion, around J1407. That helped the ring survive, but created new problems. The simulations found that an 11-year orbit with a companion in roughly the 60 to 100 Jupiter mass range could preserve a retrograde structure for many orbits. That pushes the central body deep into brown dwarf territory and partly into the low-mass star boundary, overlapping or exceeding observational limits from imaging and radial velocity. It also raises an origin problem. Young disks normally inherit prograde rotation from the system in which they form. A vast retrograde disk might require capture, disruption, or another unusual history. A later 2022 study added the self-gravity of a massive disk and tested a lower 20 Jupiter mass companion. Every prograde model was strongly disturbed during the first orbit. Retrograde disks survived better, especially at lower eccentricity, but the highly eccentric cases needed to explain the original transit lost material rapidly on century-scale timescales. Even the surviving models continued shedding mass at each close approach. The same simulations challenged the famous exomoon interpretation. A massive, repeatedly disturbed disk developed spiral structures and temporary density gaps. In one retrograde model, a gap appeared near the same 0.4 astronomical unit radius as the gap inferred from the 2007 light curve, even though no moon was present. The feature later disappeared. A dark lane in the reconstructed rings could therefore be a transient product of tidal disturbance rather than a path cleared by a satellite. The simulations also found that repeated gravitational stirring raised particle speeds and made calm, in-place moon formation difficult. This does not prove that no moon could exist. A captured moon, a moon formed earlier, or a different disk configuration could behave differently. It does mean that the simple picture of a stable young ring smoothly building moons is not the only interpretation, and may not be the most dynamically natural one for a highly eccentric bound orbit. By this stage, the proposed system required several things at once: a companion that had evaded every direct search, an orbit that had not repeated in the observations, a disk filling an extreme fraction of its gravitational territory, and possibly retrograde material surviving repeated close passages. That led to a radical alternative. Perhaps the occulter was never bound to J1407, a free-floating planet or brown dwarf carrying its own dusty disk could have crossed the line of sight by chance in 2007 and continued through space. A one-time alignment predicts exactly what astronomers saw: one eclipse and no return. The probability of such a precise chance alignment is low, but a rare event can be observed once, especially when surveys watch millions of stars. The free-floating explanation had one great advantage over the bound model. It did not need the eclipse to repeat. For years, it remained an idea without a detected object. Then ALMA appeared to find one. What ALMA found, then lost. The Atacama Large Millimeter Submillimeter Array, known as ALMA, does not search for visible rings. It detects faint emission from cold material at millimeter wavelengths. If the 2007 occulter carried a massive dusty disk, ALMA offered a way to find the dust even when the central object was too faint to see. In 2017, ALMA observed the field around J1407 in band 7, near 345 GHz. The star itself was not surrounded by a bright millimeter source at the expected position of a bound ring system, but the image contained an unresolved point of emission offset from the star. Depending on whether one quotes the fitted or peak value used in the two papers, the signal was roughly 80 to 90 microjanskis. It was only about a 4 sigma detection, faint but potentially meaningful. Its position was not consistent with a normal companion simply sharing J1407's proper motion on the proposed close orbit. The 2020 study considered several explanations. The source might be a distant background galaxy. It might be a statistical noise fluctuation. Or it might be the actual eclipsing body, no longer near the star because it was never bound to J1407. In that third scenario, a free-floating object surrounded by warm dust had crossed J1407 in 2007 and moved to the offset ALMA position by 2017. The geometry was intriguing. The separation between the star's 2007 location and the millimeter source was broadly consistent with the high transverse speed inferred from the sharp eclipse gradients. A free-floating disk could explain why the eclipse never returned. The ALMA flux could be produced by optically thin dust around a low-mass substellar object, but the evidence was not complete. The source was unresolved and seen at only one epoch. The accompanying NACO infrared observations in 2019 did not reveal a planet or brown dwarf at its position. The authors therefore left both the free-floating interpretation and the background source interpretation open. Most importantly, the free-floating hypothesis made a testable prediction. If the 2017 source was the body that crossed J1407 10 years earlier, it had a specific apparent motion across the sky. By 2024, it should have moved to a new predicted location, still inside a single ALMA field. A persistent background galaxy should instead remain at the original 2017 position. ALMA returned between the 26th of June and the 13th of July 2024. The new observations used a comparable wavelength and achieved an image noise of about 17.5 microjanskis. Nothing appeared at the predicted moving position. Nothing persisted at the original 2017 position. If the source had remained as bright as before, it should again have been visible at roughly 4 sigma. It was not. The simplest interpretation is that the original feature was a noise spike. The authors also allowed the less simple possibility of a genuinely variable or fading millimeter source. A steady background galaxy became difficult to explain because it should not have vanished. The result was released in December 2025 as a research note of the American Astronomical Society. The abstract says the team rules out a dusty object as the cause of the 2007 eclipse. That sentence needs context. The observations directly remove the 2017 ALMA point source as the persistent moving object proposed in 2020. They also rule out the thick, millimeter bright disk models dominated by grains larger than about 1 millimeter that had been favored to explain that source. There is no surviving ALMA detection of a free-floating ring body. What the result does not do is erase the original eclipse. It does not show that no dust crossed J1407. It does not prove that every possible thin disk, low-mass ring system, or structure dominated by smaller grains would have been bright enough for this ALMA observation. And it does not directly rule out every possible bound companion. Those broader conclusions would require additional assumptions about dust temperature, particle size, disk geometry, and location. The most accurate statement is therefore narrower and stronger at the same time. The best physical candidate produced by the 2017 mm data did not survive the follow-up test. The free-floating, millimeter-bright dusty object associated with that source is no longer supported. This is how science is supposed to work. A tentative detection suggested an explanation. That explanation predicted where the source should appear later. The team looked. The prediction failed. The hypothesis lost its evidence. But the disappearance created a deeper problem. The bound companion had never been detected. The eclipse had never repeated. The dynamically stable ring models required difficult conditions. And now the one offset source that might have represented an unbound occulter was gone. Nearly 2 decades after the event, astronomers still had the same piece of undeniable evidence they began with. A star that lost almost all of its light in a complex pattern for nearly 2 months. They still did not have the object that caused it, the mystery that remains. So what remains? The first possibility is still a bound secondary object surrounded by a large disk or ring system. This interpretation explains the sharp edges and repeated structure inside the 2007 light curve better than a single solid body. But it now occupies a restricted and uncomfortable part of parameter space. The companion must have escaped direct imaging and radial velocity detection, avoided producing another observed eclipse, and carried material that survived a dynamically demanding orbit. A lower mass companion on a long or unusually eccentric path might still hide. A thinner disk, a disk dominated by smaller grains, or a structure much fainter at ALMA wavelengths might also escape the latest millimeter limits. None of these versions has been detected. They remain possibilities, not discoveries. The second possibility is an unbound object. The specific free-floating source proposed from the 2017 ALMA image is no longer supported, but a different undetected object could, in principle, have crossed the line of sight once and continued away. This neatly explains the absence of repetition. It also requires a rare chance alignment and currently has no identified body attached to it. The third possibility is a different kind of extended natural occulter, a clumpy circumsecondary disk, a transient cloud produced by collisions, or another structured concentration of dust whose geometry was not captured by the famous 37-ring model. The data require large-scale obscuring material with sharp changes in opacity. They do not uniquely require 37 circular rings around a planet. A purely stellar explanation is not persuasive. J1407 is active, but its normal starspot variations are only a few percent. The eclipse removed about 95% of the light and contained rapid, repeated edges. The original researchers compared independent survey data and nearby stars. The event was real, and external obscuration remains the scientific foundation of the mystery. There is also no evidence for an artificial object. Nothing in the light curve requires technology. Natural disks, rings, debris, and dusty companions are already known to create deep and complex eclipses. The uncertainty concerns which natural structure crossed the star, not whether the event was engineered. J1407 is not alone in teaching this lesson. PDS-110 appeared to show 2 similar eclipses separated by a regular interval, leading to a prediction that a disk-bearing companion would eclipse again in 2017. A worldwide campaign watched the star, and the predicted eclipse did not occur. The events were later judged aperiodic. VVVWIT08 underwent a single deep long-duration dimming that may also have involved a large dusty disk around an unseen companion. Other modern surveys are finding additional stars that fade for months or years behind enormous structures. At the same time, the broader idea of circumplanetary disks is real. In the young PDS-70 system, astronomers have directly imaged forming giant planets, and millimeter observations have found compact dust associated with PDS-70c that is interpreted as a moon-forming circumplanetary disk. J1407's proposed structure was extreme and unconfirmed, but the physical process that inspired it is not fantasy. Young planets really can carry disks where satellites may form. This is why J1407 remains scientifically valuable, even if the original Super-Saturn picture proves wrong. The event forced astronomers to develop methods for reading complex occultations, modeling tilted disks, testing ring stability, searching photographic archives, and coordinating follow-up across optical, infrared, and millimeter wavelengths. It exposed the difference between a beautiful reconstruction and a direct observation. That difference should be stated without ambiguity. The star J1407 is real. The 56-day eclipse in 2007 is real. The loss of more than 3.3 magnitudes of light is real. The rapid gradients and internal structure are real. The 37 rings are a model. The radius of 0.6 astronomical units is a model. The estimate of roughly 100 lunar masses is a model. The gap and its possible exomoon are interpretations of that model. The object called J1407b has never been directly detected. No second eclipse has been found. The 2017 ALMA source did not reappear in 2024. That is the evidence as it stands. What could settle the mystery? The clearest answer is another eclipse. A repeat with continuous modern coverage would reveal whether the event is periodic and would provide a vastly better light curve. Multiple observatories could measure the eclipse in different colors. Spectroscopy could identify the size and composition of the dust. Space telescopes could observe without daylight gaps. The timing would constrain an orbit instead of forcing researchers to guess one from a single event. Repeated wide-field monitoring is now better than it was in 2007. The Vera C. Rubin Observatory began its 10-year legacy survey of space and time in June 2026 and is repeatedly imaging the southern sky, where J1407 lies. Rubin may catch a new event in J1407 or discover other systems whose eclipses can be followed from the beginning rather than reconstructed years later. Future Gaia data releases may place tighter astrometric limits on massive bound companions. Deeper searches with the James Webb Space Telescope, extremely large ground-based telescopes, and future millimeter observations could reveal a faint object or further restrict what can hide near the star. None of these instruments guarantees an answer, but together they can keep shrinking the unknown space. And if the eclipse never repeats and no object is ever found, J1407 may remain a one-event mystery. Astronomy contains events that happened before we understood their importance and could not be recreated on command. The honest response is not to turn a model into a fact. It is to preserve the evidence, test every prediction, and allow uncertainty to remain where the universe has not yet supplied an answer. The final verdict is therefore both simple and unsettling. Something enormous and structured crossed J1407 in 2007. The ring system interpretation was a serious and ingenious attempt to explain the light curve. It may still contain part of the truth, but the famous planet with rings 200 times the radial extent of Saturn's is not a confirmed world. It is a hypothesis built from one incomplete eclipse. Perhaps a young companion carried a vast moon-forming disk. Perhaps a free-floating body passed between us and the star. Perhaps the light curve recorded a different dusty structure that no current model has fully captured. We do not know. J1407 dimmed once, and the object responsible disappeared without giving astronomers a second chance. 18 years of searches have transformed a spectacular claim into a more honest and more interesting mystery. Not the story of the largest rings ever discovered, but the story of how much can be inferred from starlight, how easily an inference can become an image in the public imagination, and how science responds when the object behind the image refuses to appear. The giant ring planet may exist in some hidden form. It may have passed through only once, or it may never have existed in the way we pictured it at all. For now, J1407b remains a question written across the light of a distant young star. Thank you for spending this time with Beyond the Surface Cosmos. If this mystery changed the way you think about discovery, please like the video, subscribe to the channel, and share it with someone who loves the unanswered questions of space. Your support helps us keep exploring them carefully, one piece of evidence at a time.